Hello everyone, and thanks for joining. If you're ever dealing with big data, especially with time series data, you might have come to a point that the data becomes too big, maybe even bloated, to a point that the system is getting slower and slower as the data becomes bigger and bigger. Then, maybe some of you heard of the word cardinality. What is it, and what do I do with this high cardinality data? My name is Asaf. I'm a software engineer at Singular, and today I'm going to talk about high cardinality. What is it? Why do we care about it? And how we, in Singular, improved our pipeline and API efficiency by understanding the data. Now let me say a word about Singular, what we do, and why we even had to deal with high cardinality data. So we help brands. Some of them you can see in this slide. We help them grow faster by collecting all the marketing data from many data sources, and we combine it into a single dataset. This gives our customers the ability to view their data aggregated, but with as many breakdowns as they want in a single source of truth. As a marketing data platform, we process user-generated events such as ad clicks in mass volumes. So as our operation scaled, we started to experience slowness in our system due to those really large volume of data. In addition, we often see huge and unexpected spikes due to click spamming and other types of fraudulent activities. In a word, click spamming is when fraudsters sends high volume of clicks for the chance of a misattribution and a potential payout. We're talking about millions of events that enters our system in a very short period of time. So we wanted to reduce the volume of the data, and we didn't want those extreme cases like click spamming to affect our user experience. Now, before we dive into talking about cardinality, I want to demonstrate a little bit the effect of adding more granular dimensions, more breakdowns, giving the data a higher resolution, and by that increasing its volume. So let's take a look at a simple example. We have here game type cards with three game names: Solitaire, War, and Poker. Now, let's add another level of data. Country level, for example. So I added here Israel and the United States. But what happens if I add all the countries, like 200 countries? And now let's add another level of data. Operation system. So I think you get the idea. And I only added two unique values each time. So think of what would happen if I add another column that the user controls its value. The number of unique values in this column can be even tens of thousands or hundreds of thousands of unique values. In this case, you might get millions of rows for a single game. So let's talk about the effect of this large volume, high resolution data on our system, and some of the naive solutions that we have tried. So the first thing would be the effect on our ingestion, the performance of our pipeline until the data reaches our database. So you might have think, yeah, an immediate solution can be to scale our system, right? So we have tried that, but first there are two main things that we need to consider before we can scale our system. The first thing is that it costs money, and sometimes a lot of money. And the second thing is that scaling depends on your architecture. If your architecture is built for scale, it might be easy, but if it's not, it might be a complicated task. And in addition to that, when you add more resources, then yeah, you will get to a point that your system is stable and steady. But what if your business continues to scale and your operation continues to scale? Then those extreme cases, such as click spamming we talked about, will become more frequent and the system becomes slower again. And then you need to scale again and again and again, and that's not really feasible. Now let's talk about API performance. So once the data entered a database, the user is now able to query the data using our API. And we want to give our customers a good user experience and a fast API. But if we need to return a large volume of data with many dimensions and many different breakdowns, returning the results can become slower. So one simple solution would be to use pagination, which is a good solution. But yet, when the data is very granular and includes many dimensions and many breakdowns, and you want to perform an aggregated report, it is possible that this calculation will become slower. And we want to give our customers a fast and aggregated report. And another possible way to solve API performance is to put a hard limit on the number of rows returned and aggregate the rest of the results into a single value like other. And this is exactly what Google Analytics is doing. This gives you a spoiler about cardinality. Google here is limiting the cardinality of their reports to give a faster API. Now, I just want to make sure all of you understand what cardinality actually means. I guess that most of you didn't really know the meaning of cardinality until you really had to deal with it, or if you had to deal with some big data databases. So, cardinality is the number of unique values in a column. As you can see in this example, we have here game type that has two unique values, cards and classic. And we have game name that has 6 different unique values. But usually we don't talk about cardinality with numbers. We talk about it with low and high. Now think for example of cities or even street names or bank account. The number of unique values can become extremely high. So the approaches I mentioned before of scaling to improve our pipeline performance or pagination to improve the API performance weren't really good enough for us. We wanted to find a better and permanent solution that will improve both our pipeline and our API performance. So we went to do some research. We started with diving into our data itself. We tried to understand how our data behaves and how it distributes. We talked with customers and we learned how they actually use their data. And by understanding that, we were able to create our Cardinality Protector, which now reduces the cardinality and it saves us an average of 30% of the data without actually interfering with the customer's data and their day-to-day use. This improvement actually gave all our customers even a better user experience. So I want to start with the research we did. So let's dive into the data. Now, as I said, we collect events from many data sources. Now, we collect those events into a batch of constant time frame. For this example, let's take 1 hour. And this is how it looks. This is a batch of 1 hour events that we get from many different data sources for all the apps. So what do we have here? We have here 3 types of events. We have impressions, which is when the user saw the ad. We have clicks, which is when the user clicked on the ad. And we have install, which is when the user installed the app or the game. As you can see, the events are currently sorted by the time they entered our system, which makes sense. And what else do we see here? We have here game name and the device, and we also have the keyword dimension, which is the search term that the user used when he saw or clicked on the ad. And since the keyword that led to the click or the install is only relevant for a single app or device, we wanted to partition the data into some logical blocks. So we sorted the data, we took the batch and sorted it into those partitions. Like this. The data is now partitioned by game and device. Then, we took some partitions, mainly those with the high volume, and we tried to understand why the data became that big and that bloated. So, let's take a look at a single partition, a single block, like Solitaire and iOS, for example. We saw that some dimensions in those partitions have extremely high cardinality, like we see in this keyword dimension. So, what we did is we took a closer look at those dimensions, and we tried to understand how the data in those dimensions behaves, how it distributes. So how we did this? We created a histogram of the appearance frequency of each one of those keywords value. And this is what we got. As you can see, most of the values here are solitaire, solitaire with a typo, and cards. But in addition to those, we have more values that their appearance frequency is much lower. Like someone searched for watermelon and somehow got to the solitaire game ad. It's interesting, but maybe not interesting at all. In a real situation, the data in those high cardinality dimensions is distributed the same way. We saw that in most cases, we get a long tail distribution, like this one. Now, what if we say that maybe some of the values in this long tail are not really important, and that we can drop them and combine them into a single value? So let's take a look at how the data for each one of those keywords sums up. If we sum up and aggregate all the events for solitaire in iOS, this is what we get for each of the keywords. And I want to talk about the metrics, installs, clicks, and impressions. So for marketers, installs is the most important metrics in this case. This is usually what they are actually paying for. And in most cases, install leads to revenue. So if that's the case, we want to give priority to installs, right? Same thing goes between clicks and impressions. It's more meaningful for the marketer if the user clicked on the ad than if he only saw the ad, right? So as you can see, we sorted the keywords we got first by installs, then by clicks, and only then by impressions. So as you can see here, cards have more impressions than solitaire and solitaire with a typo, but it has less installs, so it will come after. Now, remember that our goal here is to aggregate and reduce the amount of rows. So let's take a look at the values in the long tail that we previously saw. We can see that the values in the long tail here don't have any install, and the number of click or impressions is very low. There's almost no traffic or any meaningful traffic for these values. So let's group them together. But first, we need to decide what is our limit. How many keywords do we want to group together? Or how many keywords do we want to keep? So if we decide to keep only 5 values, we can do this and aggregate all the 120 watermelons into a single grouped value. Or if we decide to keep only 3 values, this even saves us more. So what we saw here is what we actually do for all the high cardinality dimensions. We will aggregate the events per value, sort by metrics importance, and then group the values in the long tail. So what we just saw is basically the logic of our Cardinality Protector. So if we go back to the original batch after it's sorted and grouped, I want to go over the terms and what is required in order to run Cardinality Protector. So game and device, these are the dimensions we group the data by. We call those the unprotected dimensions. We don't run cardinality protection on them. We group the data by them. And we have the dimension that we do want to protect from. Those are called the protector dimensions, the dimensions that we want to protect from high cardinality. In addition, we saw that some metrics are more important than others. So after we aggregate, we want to sort by installs, then clicks, and then impressions. And last, we need to define the threshold. How many values do we want to keep for each one of those dimensions in each partition? And note that the threshold can be different for every dimension we want to protect. Now, let's do a zoom out and do a quick recap of what we had here. So first of all, we get many events from many data sources, and they are all added into a single timeframe batch. We then sort this batch and split it into those logical blocks or partitions we talked about, the game, and the device. We then run the Cardinality Protector logic we just saw on each one of those partitions. And lastly, we take all the results and we combine them into an aggregated, combined, and protected batch. We are running this logic at an early stage of our analytics pipeline. This gives us the ability to improve our pipeline duration and efficiency. It helps us improve and reduce heavy memory tasks. And the main thing is that we are not prone to extreme cases like click spamming that previously affected our system performance. Now for the fun part, let's see some code. First, I want to show you how easy it is to do the Cardinality Protector logic with pandas. I am not going to get into optimizations of pandas. There's a whole other talk about it in PyCon this year, so go hear it. We have the metrics order, the installs, clicks, and impressions. And we have threshold, which is constant here, but you can of course make it constant per dimension, or even dynamically changed. We have the protected dimensions, keywords in our example. And now, assume that we loaded a partition into a pandas data frame. And for each dimension we want to protect, we check if it is above the cardinality threshold we just did. If not, we skip it. But if it is, we want to protect it, right? We first aggregate the events and then sort it by the metrics order list. And after it is sorted, we override all the values that are above the threshold with this group value. This will make it possible to aggregate them and reduce the amount of rows. So what you see here is actually a simplified version of our Cardinality Protector code. Another thing I'd like to show is actually one of the challenges we had, sorting the data. We wanted to be able to run a fast and memory efficient sorting on those huge batches. So we first used Python methods like pandas, but they weren't really good enough and fast enough. We tried to find something that will be both memory efficient and really fast. And we ended up using Unixsort. Yeah, not Python, but it's a very powerful tool. And this is how you call it from Python. For those of you who are not familiar with it, Unixsort is an extremely fast disk-based sorting tool with a constant memory overhead. As you can see in this command, we give it an input of a CSV file, and we tell it to sort the data by the first two columns, as you can see in the K argument. In addition, in the S argument, you can see that the maximum memory that will be used is only 500 megabytes. Now that the data is sorted, we can iterate over the file and read each block or partition. We open the file with CSV, and then we can use Python iter tool to group the data and get a single partition each time. And by that, we can run the Cardinality Protector logic we just saw on each one of those partitions. Now, I want to show you some of the results we get from running the Cardinality Protector. So here are some real results from our monitoring dashboard. You can see here the top 10 average save rates by customers. Yes, those are real numbers. For some customers, we save up to 87%, which is mostly fraudulent data that is coming for click spamming. And here you can see the average cutoff value over all customers. What this means is that we are almost not grouping values that contains cost or install. We only group values that contain some clicks or some impressions. So hopefully you find this session useful and interesting. And if you decide to take only one thing from it, take this. Learn your data, understand your audience and your customers. It will give you power. That's it. Thanks for watching, feel free to reach out, and see you next time.